Hey, and welcome back. And this section is going to all be about rate concentration graphs. So strap in, this is a bit of a wild ride. So take a look at these three graphs, the top three. Now these are all concentration time graphs for a zero order, first order, second order, like we've done. But in this section, I want to talk about a different type of graph. So instead of the concentration against time, and that would perhaps show the reactants decreasing or the products increasing, it shows how the rate of reaction depends upon the concentration. So it's no longer time dependent, and you can see the differences between the zero order, first order, and second order. And I want to go into that in more detail and show you what we can find from each one of these graphs. So the first one we want to look at is a zero order reaction. You can see we've got rate on the y-axis and we've got concentration on the x-axis. And you can see that there's a little flat little line that goes along and the rate is constant no matter what the concentration. It's a flat line. Having more concentration has not increased the rate. So if we were to look at the equation for this line in the form of y equals mx plus c, the first thing we'd notice is that the gradient of this line is equal to 0, which means that m, which represents the gradient, is also equal to 0, and mx is still equal to 0 if m is equal to 0. Which means the equation y equals mx plus c just becomes y equals plus c. So the mx bit has gone away. Now that means that the y, which is the rate, is only dependent upon well, not the concentration, it's independent of the concentration. It's dependent upon the rate constant only. In fact, the rate is going to be equal to the y-intercept of this graph. So I can find that the rate is equal to the rate constant for this type of graph. For a first order graph, the thing that you need to look at is the fact that this is a straight line, but it's going up at some sort of gradient. Also, notice that its intercept is going through 0, which means when there's no concentration, there's no reaction, as you'd expect. So in the form of y equals mx plus c, with no y-intercept, basically the plus c is 0, which means we've got a graph of the type y equals mx. Now if we have a look at what y and x represent, y represents the rate and x represents concentration, so what does the gradient m represent? Well, we know that rate is equal to the rate constant k times the concentration. Therefore, k, the rate constant, is going to be equal to the gradient of this graph. So here's something for you to try. There's two reactions here, reaction 1 and reaction 2. And there's the concentration, which you'll plot on the x-axis, and then there's the rate, which you'll plot on the y-axis. So the very first thing that you can do is to plot this data. See the shape of the graph. If it's a flat horizontal line, then it's 0 order. If it's a straight line increasing, then it's a first order. And from both, you should now be able to work out the rate constant k, remembering that the intercept, the value of the rate on a 0 order is equal to the rate constant, and on a first order it is the gradient of the concentration rate graph. Slightly more problematic for us are those pesky second order reactions, because even a rate against concentration graph is not going to be a straight line, and a rate concentration graph by itself can't really tell us very much, other than identifying that it is in fact a second order or higher reaction. But what we can do is, if we take each of those concentrations, as you can see in the data given below, and we square it and then plot the rate against the concentration squared, at that point we do then get a straight line. And the straight line has a gradient equal to k. So here is the case that k of this data is equal to 0.05, and plotting y equals 0.05, x squared produces the original rate concentration graph, which gives us some confidence that the rate constant is equal to the gradient of the rate concentration squared graph. So here is a third reaction, and you can have a go plotting this data. It is a second order reaction, and what you will have to do is first plot a rate concentration graph to prove that it is second order or higher, and you're looking to see that it's a curved line. And then for all of those concentrations of Z, I want you to square those and plot those against the rate. Find what the gradient of that graph is, and then use that to determine what the rate constant is for this reaction. And also, it's good practice to give the unit too. Now, it is possible graphically to determine whether or not the order is second order or higher. In fact, it's possible graphically to figure out what order it is. And the way to do that is to plot a log-log graph. So basically what you would do with your raw data is you take log to the base 10 of all of the concentrations and log to the base 10 of all of the rates. Now, you know that this reaction is going to have a rate equal to rate constant K multiplied by the concentration to some power n. And that power n is the order of this reaction. So it's 2 when it's second order, 3 when it's third order, etc. Now, when you plot any kind of power law on a log-log graph, it draws a straight line. And the properties of that straight line tell you about the order of the power law that you've used. So we can use it here. The straight line as drawn here, this is reaction 3. This is the one that you've just drawn out. The log of the rate is on the y-axis, and the log of the concentration is on the x-axis. And you can see I've got a straight line of data points. Now they're in the format that the log of the rate is equal to n, the order of the reaction, multiplied by log of the concentration plus log of the reaction constant, or the rate constant. So what does this graph tell us? Well, the gradient of this graph tells us the order. So when the gradient is equal to 2, then this has a rate equal to Ka to the 2. If the gradient equals 3, then the rate equals Ka to the 3 in its third order. And the intercept also tells us log of K, which means rearranging that 10 to the power of the intercept would give us the value of K. Now these rules are quite complex, but I recommend you have a go at drawing one of these out and extracting, first of all, what is the order of this reaction, and secondly, what is the rate constant. And indeed, here is an opportunity for you to try it out. So we've got the concentration of W there, and we've got the rate at which the reaction was taking place. And what you need to do is take the log to the base 10 of all of those concentrations, log to the base 10 of all those rates, plot the log of the concentration on the x-axis against the log of the rate on the y-axis. It should be a straight line. And with that straight line, the gradient is going to represent the order of the reaction. And remember that 10 to the power of the intercept is going to give you the rate constant. So have a go. Can you work it out?